Hi guys, let's begin our look at the concept of aromaticity. You have seen aromatic compounds since the beginning of Organic 1, where we saw all the time the classical benzene ring, the most common aromatic ring. We gave a sort of a limited definition of aromaticity back then, which involved every atom having a p orbital. If you remember on the functional group list from my Organic 1. But we really haven't talked about the idea of aromaticity to any degree. We'll now do that here in Organic 2. We have two handouts. One is shows some warm-up questions here. Some very important questions: planar, non-planar, aromatic, anti-aromatic, or anti-aromatic. What does that mean? Versus non-aromatic. Okay. Understanding the p orbitals, pi systems. Dealing with rings other than a 6-membered ring, benzene ring. This is an 8-membered ring with 4 pi bonds. Dealing with ions that may or may not be aromatic. Okay. What type of experiments can we use to study aromaticity? All right. We also have an outline. Structure and reactivity of aromatics. Mine is green here. We will begin with the structure of benzene. Okay. And the second page in this handout shows some common drugs with heterocyclic rings. Okay. As we will see, the benzene ring is all carbons, a so-called carbocycle. A heterocycle has a heteroatom. Hetero meaning non-carbon, different from carbon. And so this here is a heterocyclic ring because one of the atoms in the ring is a nitrogen. Okay? That is a heterocyclic ring. This molecule has 2 heterocyclic rings and a carbocyclic benzene ring. One of these rings is aromatic, one is not. We need to be able to quickly recognize that. But there's actually a large variety of heterocyclic rings. Many of them are aromatic. They can be called heteroaromatic rings, but some are not. Many are not. These are some examples. As we go along, we'll point some of these out. Like thiophene ring. You've seen a pyridine ring before. We actually use just simple pyridine itself as a weak base sometimes, such as in the pocyl-pyridine reaction, dehydrating an alcohol with pocyl and pyridine. These are also some fairly common drugs. Lipitor is a very important drug. It has a pyrrole ring as the central ring. Okay, reference page there. All right, let's get into it. Intro to benzene and aromaticity. This is sort of where we're beginning. Here's benzene, 3 pi bonds. Sometimes my pi bonds are not exactly shown in very precisely. All right, as you draw them quick, formula C6H6. We see it has 4 degrees of unsaturation, both from structure and formula. Benzene is a liquid, has a boiling point of about 80 degrees Celsius, with water being 100 degrees, so the boiling point's lower than water. It's actually a pretty good solvent, but you don't see it used much these days anymore because it is a carcinogen. It's known to cause cancer. All right. Why? We may talk about a little bit later. Instead, toluene Okay. Toluene is going to be preferred over benzene usually. Toluene, of course, on the nomenclature page, toluene is where the benzene has a methyl group. And that one methyl group makes it less toxic. We may discuss why later. Benzene was first isolated in 1825 from whale fat. Back then they used to burn whale fat in lamps, including street lamps. And they soon discovered that a residue was sort of emitted from that. And if you condensed that vapor, you could condense a liquid, and within that liquid you can eventually purify out benzene. Now, whale fat probably does not contain benzene, but upon heating the whale fat, the organic molecules probably decompose, or no doubt decompose, and benzene is a byproduct of the combustion of the whale fat. Now, keep in mind that in 1825, they could isolate a liquid and purify it, but they had very little idea of structure back then. In fact, the structure of benzene was not determined until maybe 40 or 50 years later. And keep in mind that the double bond, the carbon-carbon double bond, was not even proposed until about the 1860s. So they had little structural information. They could determine formula back then. They could determine a CH empirical formula. Okay? They didn't know if it was C4H4 or C10H10. But it appeared to have an equal number of carbon and hydrogen atoms. They could do that back then. Now, actually, one of the original proposed structure of benzene was, and there were many, one was this structure here, which you see it has no carbon-carbon double bonds. It's actually two 3-membered rings sort of bonded together on each side. Today, that's called prismane. You can look that up on Wikipedia or find information about it. But at some point, this structure was proposed, and soon that was confirmed. And that's a long story. By the way, Michael Faraday was involved in the isolation of benzene. You may know him from your physics courses. He's often claimed to be a physicist, but Faraday also did chemistry. Okay, structure of benzene. Of course, each carbon is sp2. Okay. Each carbon is thus sp2, trigonal planar, bond angles of 120. Here I'm showing the sigma framework, just the sigma bonds. There we can see the 120-degree bond angle around this carbon. It's also planar, flat on the paper. That is, the bonds are not coming forward or back, they're all flat on the paper. Or if you held it up like this, it'd be flat on the board. Okay. Now each carbon also has a p orbital. Okay, right, sp2, 3 hybrids, 1 p orbital. And here I'm showing just the p orbital on each carbon, and we can consider that the pi framework, or the pi network. 6 p orbitals. Now each p orbital is going to have 1 pi electron. All right. You should know this by assessing the structure. If we just look at this simple structure, we see pi bond, which would be 1 p orbital and electron overlapping with 1 p orbital, and so we have pi bond. Okay. I'll do pi bond here. Then we can say that these two are overlapping to make pi bond there. And then these two are overlapping to make pi bond there. And that would be the 3 pi bonds that we see. And so understanding what you see would lead you to understanding that you have thus 6 p orbitals here, leading to these 3 pi bonds. All right. But let's look at this. I chose to say that these two were overlapping, those two and those two. That would put pi bond here, here, and here. I'm going to try to change color here. What if instead I said these two were overlapping? Okay, these two were overlapping, and these two were overlapping. That would put pi bond here, here, and here, right? Well, which is correct? Actually, the answer is, well, neither is correct. What's going on here is these 6p orbitals are all interacting with each other. Okay? And I'm just going to make it all blue. Okay? They're interacting all the way around. And so you have 6p orbitals interacting in a cyclic manner. All right? We also have 6 pi electrons there. Okay, as we move ahead, we're going to, determine this for different compounds. And actually, neither one of these are correct. Really, you have pi bonding between each carbon. Now, you can't have 6 pi bonds in the ring. What you really have here is partial pi bonding between each carbon-carbon. And what that really looks like is, instead of having 2 bonds between each carbon, it's like you have a bond, okay, the sigma bond, and then maybe a half a bond. And I'll redraw this here, but it's also drawn on the page below. That is, we got a bond and a half, 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 a bond and a half. Okay? Now there I tried to make it sort of straight. Boom, boom. Okay, straight lines with my half bonds. Here I showed the same thing, but I kind of ended up with a circle of the partial bonds. All right? But this is what you really have in benzene. The electrons are said to be fully spread out here. They're fully delocalized. We say we have delocalized bonding. Now, a consequence of that if the structure was really double single, double single, double single, okay, double single, if the structure was really 3 isolated pi bonds, it wouldn't be equal all the way around. You would have, again, double single, double single. The true structure has 1.5 bonds, 1.5, half, 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 if you don't want to count the sigma bond. Okay? Well, here we're counting the sigma bond. So it would be 1.5, 1.5, 1.5, 1.5. All right? In terms of bond order, 1.5 bond order, each CC equals 1.5 bond order. That's what we have. Not bond order equals 2 and bond order equals 1. Okay, not like that. Now, because the bond order is really 1.5, bond length is all the same. Because the bonds are really equivalent. The bond length for benzene is 1.39 angstroms. You'll see that that's sort of halfway between the carbon-carbon bond length of a single bond, which would be 1.5 angstroms approximately, and a carbon-carbon double bond is typically about 1.3. So if you round this off, it's approximately 1.4, and you see it's about halfway between single bond and double bond. We also know that benzene is a nice symmetrical hexagon. If it was double bond, single, it would be an ugly hexagon because you would have short, long, short, long, short, long. So, the result of the delocalization we're talking about is all carbon-carbon bonds in benzene are the same length. and also same bond strength. That's what sort of looking at 1.5 bond order kind of tells you. They have the same bond order. Okay, little interesting tidbit here. Back in the mid-1800s, a chemist by the name of Kekulé actually thought that these two compounds should be different. That is, here the double bond is between the two bromines, and here it is not. He actually spent some time on trying to separate these two, and he never could. That's because the real structure is bond and a half all the way around, okay? And the bromines are there, okay? These are the same. They are both this. It's just one molecule. Now we typically will draw them like this. Either one is right, or actually either one is wrong. Now many people will draw benzene with a circle in it like this, okay? And then maybe you could draw benzene and say, hey, like this, and then put the bromines here and say, oh, there's no other way for these to be. I would not do this. Please never draw a circle there, okay? Even though that's real, I don't like for you to do that, because when we get to heterocyclics, you certainly don't want to do that. And if you ever try to do a mechanism with an aromatic, you need your pi bonds in there. Even though that's not the actual structure, okay? Don't we always draw benzene like this, though? Yes. All right. You need to understand the actual structure. Soon, organic chemists realize that this is just the same compound and it really exists like this. Okay. Now, we said we know it's a nice hexagon, we know bond lengths. How do we know that? Well, many ways. Okay, that's based on data. That data has been sort of accumulated over the past 150 years, okay, until a very strong case has been made. The early 1900s, or maybe 1920s, 1930s, that's when X-ray crystallography started to be fairly common. And that's really the closest we can come to seeing molecules. And we can actually see benzene rings, we can see bond lengths. This is an example of a X-ray crystal data on this compound here that is made in my research lab. It does contain two benzene rings. This gives the bond lengths and bond angles. But you see the C1, I'm sorry, not that ring. It's labeled over here, ring A. This is where you have C1 through C6. And I indicated C1 and through C6 here. Okay, and you'll see that each bond here, like the C1, C6 bond, has a bond length of, okay, if we round this off a little bit, be 1.38, yeah, angstroms. Now over here we said benzene is 1.39, and then I rounded that off to 1 decimal place. All right. Now this is not exactly benzene. Being bonded here to this ring can change some of the bond lengths a little bit, but it's very darn close. And if you look at all the carbon-carbon bond lengths in this ring, they're all pretty darn similar. All right. All around the 1.38, 1.39 range. It's a little interesting that that one's shorter. It's probably because of that chlorine there. The electronegativity of that chlorine affecting that one just a hair. But you certainly don't see any bonds that are like 1.5 angstroms and then 1.3 angstroms. So that's some actual data, and it's consistent with what we talked about over here. X-ray data. All right. And then the bond angles there, a 3-atom bond angle very close to 120. Of course, these bond angles can vary from the standard 120 or 109.5. Okay. That was, this crystal structure was, and data was obtained at Emory. I sent the compound there. All right. So, structure of benzene. I think we just went over that some. All right. Roman numeral 2, experimental evidence for aromatic versus non-aromatic. First off, we need a definition of aromaticity, a new working definition. And we can say it is an unusual stability as a result of full cyclic conjugation. Okay? That's what we showed over here. The 6p orbitals, we have full cyclic conjugation. But that leads to unique stability. All right? Or unusual stability. Well, what type of stability are we talking about? Okay. And what is some of the evidence for that unusual stability? First, A. Well, where's A? B, C. What is A? Ah, A is bond order and bond lengths. And I just showed you some experimental evidence. Because of the aromaticity, these carbon-carbon bonds are nearly identical in length. Okay? That is sort of unusual. We don't expect single-double, single-double. And the X-ray data is actual evidence of that. All right? So we can consider that A. At the same time, if we saw a compound where the bonds were alternating between like 1.3 and 1.5, we would say, this experimental evidence suggests it's not fully conjugated, not a cyclic conjugated system, and thus not aromatic. So this is data we can use to determine if a compound's aromatic. Yes. All right. Next is reactivity. Benzene has unusual reactivity. It looks like it has carbon-carbon double bonds. And again, I'll do this for the last time, but every time I draw benzene, I'm not going to draw it in so precise. All right, I'll tend to draw them quick. All right, I'll try to draw them precise in there whenever we do a mechanism, but okay, that's the 3 carbon-carbon pi bonds. It looks like 3 alkenes, but it's not. Now we know carbon-carbon and pi bonds will react with bromine. And we learned in Organic 1 that alkenes will undergo an addition reaction to get a trans dihalide like this. But not benzene. Instead, benzene reacts with bromine to give a substitution reaction, not addition. All right, substitution. That means something's replaced. H replaced, okay? Because look, this is C6H6, this is C6H5Br. One of the H's has been substituted. Only one bromine is incorporated into the molecule. The other bromine ends up teaming up with that H and we produce HBr. Up here we did not produce any HBr. So, it looks like carbon-carbon pi bonds, but it has unusual reactivity. It reacts by substitution instead. Also, it doesn't react as quickly. Alkenes react pretty quickly with bromine to give addition reactions. Benzene reacts slower with bromine, and you often have to include a catalyst, such as iron metal. We'll talk about this mechanism. Another unusual reactivity, a bit of unusual reactivity, is the carbon-carbon double bond doesn't react with oxidizing reagents such as osmium tetroxide or KMNO4. Maybe you're looking for one of the alkenes to form a vicinal diol. Well, guess what? Benzene doesn't react with these reagents at all. Now, as an aside, you actually can get benzene to react with them. We're not going to talk about that, but just standard reaction, it doesn't react. Very sluggish. So certainly it's not just three alkenes, and we should never refer to these as alkenes in this ring. Pi bonds is better. You can refer to them as carbon-carbon pi bonds, but not alkenes. Okay? So it's a bit of unusual reactivity for carbon-carbon pi bonds. In both cases, the diminished reactivity indicates that the benzene ring is fairly stable. It's reluctant to react. It's happy as is. Okay. Unusual reactivity compared to alkenes is really what we were looking at here. All right, C. Heats of hydrogenation. By the way, we can go back up here. If you think you have an aromatic compound, well, you could react with bromine. Does it give an addition reaction? Or does it give a substitution reaction? Because aromatics typically give substitution reactions, and we didn't know why, but why? Because with substitution, the aromatic ring remains intact. If we do an addition reaction, these two carbons are now sp3, okay? There are H's here. Those two H's are still here. And since they're sp3, we no longer have a fully cyclic conjugated system of p orbitals. Okay? So it's no longer aromatic. Typically, aromatic compounds want to maintain the aromaticity. In terms of energetics, transition state leading to this product is lower than transition state leading to the higher energy product. That's a lower energy product. It's aromatic. It has an unusual stability, which implies it is lower in energy. Okay, in terms of energy, if you hydrogenate an alkene, as we saw in organic 1, such as with hydrogen and like palladium on carbon as a catalyst, we can get cyclohexane. Okay, addition of two H's, hydrogenation. We know that this is an exothermic reaction as we convert one pi bond into two new sigma bonds, and we release 118 kilojoules per mole. If you do the same reaction with cyclohexadiene, that would be cyclohexene. This would be cyclohexadiene. You can reduce both double bonds down to cyclohexane, and you release 230 kilojoules per mole, also exothermic. But note that it's not double 118. It's not. Double would be 236. Why is it not 236? Well, actually, we can add in here, and that's a diene. We can add this diene. We get the same product. Okay, we need 2 equivalents of hydrogen. Here we would get about 236 kilojoules per mole. Closer to the double. Why is this less than double? Well, do these two start at the same place? No, one of these is more stable. The conjugated diene is more stable than the non-conjugated diene. Remember, conjugation is a stabilizing factor. So it sits at a lower level, it has less energy to give off. Now it's not much of a difference. Okay? But it's more stable than that one. It has less energy to give off. I'm actually surprised it's not more like about, I don't know, 210 or so. Okay? But those are the numbers. My explanation does predict the trend we see here. Now, if you go to benzene with 3 pi bonds, first off, you need a much stronger catalyst. Palladium, nickel, platinum, those we saw in Organic 1, typically doesn't work here. That in itself tells you that benzene is more reluctant to being hydrogenated. Why? Because it has an unusual stability. It's quite happy being benzene. Also, now you can hydrogenate it with more active catalyst. In some of the rhodium and ruthenium, those actually are more active hydrogenation catalyst. And typically you often see higher pressure here. We can hydrogenate, but it turns out that we get 205 kilojoules per mole. Now we don't get 118 times 3, which would be what? Well, 120 times 3 would be 360. We need to remove 6, 354. If this was just 3 alkenes, it should be 3 times 118. It's not just 3 alkenes. It's much more stable. It has much less energy to give off. Look, it's actually has less energy to give off than the diene. All right. Once you put the 3rd pi bond in there, we become much more stable than we anticipate based on it just being alkenes. This illustrates unusual stability. We're also starting to quantify aromaticity. Okay? Oh, by the way, I had 354 here. The difference here is 149. Sometimes that 149 is referred to the aromatic stability. All right? It's much more stable than we anticipated if we think it's just 3 alkenes. All right. Heats of hydrogenation. D, NMR. What do we know about aromatic signals, protons? They appear in the 7 to 8 region. That's different from the alkene region, which is about 5 to 6. So this is not just 3 alkenes. All right. Now, if you had cyclohexene, well, drawing the H's, okay, you would expect 5 to 6 ppm. It's an alkene, right? Once you get the 3 pi bonds in there, it becomes aromatic, a fully cyclic conjugated system, and the NMR value or peak position will actually move downfield a bit. Thus, this position is an indicator of aromaticity. All right. Now, why does it move downfield? can actually look over here. And if you put benzene in the presence of an external magnetic field, such as in an NMR magnet, and this indicates the external field direction, the pi electrons in benzene will start responding to the external field. Okay. Now, these electrons will actually induce a magnetic field. You learned some of this in physics. Okay. Magnetic fields can be induced. But it has a direction, and the direction is like this. You see the arrows. Okay. Now, benzene is laid in here. The H's of benzene are out here where this field is going this way. Okay. And this field is going the same direction as the large magnetic NMR magnetic field. Okay? So it is reinforcing, it's adding. Now, is that going to be a shielding or de-shielding effect? Okay? Well, it's going to, why am I saying shielded here? Let's look here. It's a de-shielding effect, right? De-shielding effect. It's adding to that. A shielding effect, you would be shielding, okay? Like this is sun. Over here, you're getting more of that. You're getting more sun. All right? We're not shielding the sun, you're adding to it. It's like you go outside and you get more sun. You don't say, hey, this effect is keeping sun away from me. No, it's giving you more sun. That's not shielding you, it's de-shielding you. Okay? If you added sunscreen, that would be a shielding effect. Sunscreen would give you less of this. To get less of this, you need a field that opposes it. Out here, the field does not oppose it, it's additive. I don't know if this is written. Yeah, peripheral H is de-shielded. Why does that say shielded? Am I missing something here? As soon as I get rid of the video, I'll figure it out here. Okay. I think this should say de-shielded unless I'm missing something and I'm not thinking about it here. Yeah, this is a paramagnetic ring current here. All right. I think this should say de-shielded. I'm just... All right. Let me think about that. It could be simply I just wrote it wrong, but it's been written like that for several years. Nobody has ever pointed that out. Okay, I know what it is. I know what it is. This is not a paramagnetic ring current. This actually is referring to down here. Yeah. Yeah. This down here we'll see shielding. Okay, that's what it is. If you look down here, and we haven't got to that yet. Okay, down here we have H's that are on the peripheral, but also we have some in the center. Okay, and if H's were in the center, we see that as this comes in here in the center, the field, the induced field, opposes the large magnet. And this is actually a shielding effect because it's going to reduce the net effect. It's like you're getting less sun, you're getting less magnet because something is diminishing the net field strength. Okay, let's make sure Yeah. Because this is considered a diamagnetic ring current, not a paramagnetic. All right. NMR. By the way, next is, I see nomenclature. Nomenclature covered by a different video, of course, as usual. And those have already posted there on the YouTube page. Okay, so we have some experimental evidence. NMR is an experiment. Heats of hydrogenation would be experimental data. Quantifying aromaticity. Reactivity would be sort of like qualitative data. Bond order, bond lengths would be more quantitative. Okay. Number 3, comparison of benzene. Let's start looking at other compounds, other sizes. This is our benzene 6-membered ring. This is a 4-membered ring with 2 pi bonds. Okay. And we'll finish up this video sort of right here. Let's introduce this. Now, this is called cyclobutadiene. Ring 4, 2 pi bonds. Okay? It's actually a very unstable molecule that only exists at very low temperature. If you warm it up, it'll actually dimerize, it'll self-react and give another product. Okay? Very unstable. While benzene's very stable. If you look at the structures, both are fully cyclic conjugated systems. Right? I mean, each carbon has a p orbital. If you draw them in, right? 1 electron makes pi bond. 1 electron makes pi bond. We could say, well, aren't these also overlapping? Yes. Aren't these also overlapping? Yes. Okay. And it looks like a fully cyclic conjugated system. The same idea that we saw here. So if this is very stable and aromatic, why would this not be very stable and aromatic? Well, very different. This one's aromatic. This compound is known as anti-aromatic. All right. We've already given a definition for aromaticity. We can now have a definition for anti-aromaticity. This is an unusual instability due to full cyclic conjugation. All right? Okay? Both are fully cyclic conjugated systems. So we sort of have two definitions here. Now there's a third, non-aromatic. Non-aromatic is the classification we will use for a compound that is not fully cyclic conjugated. All right? Both of these are. One's aromatic, one's anti-aromatic. Something that's not fully cyclic conjugated is considered non-aromatic. Guess what? H2O is non-aromatic. It's certainly not a fully cyclic conjugated. All right. Cyclohexane is not a fully cyclic conjugated system. It is also non-aromatic. All right. Many things are non-aromatic. All right. In the next video, we need to look at why are these two different, even though they're both cyclic conjugated systems. To give a clear explanation of that, we need to look at molecular orbital theory and do molecular orbital diagrams, MO diagrams. But we will start with a non-cyclic. We'll start with butadiene. Now, organic 1, we did not cover this much this past semester. But you should have some of the basis here. Hopefully you did do molecular orbital diagrams in Gen Chem. We'll build off of that. Okay? We'll do an MO diagram of that molecule. Then we'll do an MO diagram of benzene. Then of cyclobutadiene. And we'll make comparison. We'll come up with some rules. Remember Huckel? He actually observed these rules and kind of clarified them. Then we'll move into other size rings. Okay? Please be doing some reading in your textbook about aromaticity. We'll eventually move into ions. Okay? And heterocycles. All right. I will end this video here. We have that. Nomenclature. Okay guys, that's our first video on aromaticity.